Thanks a lot for the introduction. So I'm Nico Montali. I'm a research scientist at Waymo. And you just heard from Sonton presentation now, like what are the current problems that Waymo is facing and exciting new features that Waymo driver is um, acquiring. But now this time I want to shift the focus on how Waymo actually wants to foster and help the research community to solve these very important problems for autonomous driving. And we do this through the Waymo Open project, specifically the open data set and the challenges that we're going to go over today. Here, okay. So a little agenda for today's meeting. So we have first an introduction on the data set for the open data set and the benchmarks that are attached to this to the data sets with highlights of what changed since the last year we had the same presentation at CVPR. And then we're going to go into a deep dive into the 4 challenges that we hosted this year in the last 3 months. And we're going to have winners, a little introduction for each challenge, and winners talking about their solutions. Cool. So first of all, I would like to spend 1 minute thanking all the people that made this possible. It's been a very long journey, and all of these people put a lot of effort into it, and I'm really proud of what came out of this, and we hope like we really help the research community to advance. And there's also like many other people in cross-functional teams that are not cited in this slide, but they obviously contributed. So first I would like to start from the why. Why did we release the open data set and why Waymo wants this? So we believe that for machine learning, having data sets is one of the core important things that we need for research to function, because people need to be able to work on the same problem and share the same results and compare the results on the same benchmarks. Otherwise, it's difficult to say, oh, my method is better than yours. So we basically want to do this by releasing one of the largest and most comprehensive data sets on autonomous driving, which was collected by Waymo cars over the span of multiple years and multiple cities where we operate. As I said, this has been a very long journey. So from 2019, this was the first release of the perception data set. And up until now, we had many new features coming every year and many challenges that we hosted over the span of multiple years. And usually what we have here, it's a split between 2 main data sets, the perception one, which is usually for perception-related tasks, so detection, tracking, segmentation, and the motion data set, which is more related to prediction, planning, and simulation. So going a little bit into the details of each of these data sets. So the perception data set is mostly about sensor data. So we have LiDAR data and camera data. It has various numbers of labels for different tasks. So we have 2 and 3D bounding boxes, 2 and 3D key points, semantic segmentation of various forms. Last year, we also added the 3D road graph. So that's a map that basically you can use to align all the sensor data to an actual road. And I wanted to point out that last year we also released these 2 new formats. So one is the modular data set. Since this is a pretty big data set, it's a bit annoying sometimes to work with it. So we released this new modular framework where you can pull whatever feature you want without having to download the whole data set. And hopefully this makes it easier for people with specific tasks to make it easier for them to use the open data set. We also released the object assets data set. This is intended to help generative AI and NERF kind of system. And these are very comprehensive. So you can find all the information about this on the open website that is linked there. On the other hand, the motion data set is mostly about, as I said, prediction and behavior. It's much larger in terms of scenes. So we have 570 hours of driving with over 100,000 scenarios. And we've collected this in very different cities. So you can have a very different span of behavior from drivers and pedestrians and other dynamic agents. This is, again, mostly about 3D bounding boxes. So the output of a perception system. and the map data, the 3D map data. But last year we did release LiDAR data for this for the motion data set, and this year we are releasing camera embeddings. I'll go a little bit more into the details of that because I think it's really important. We've seen a surge in end-to-end methods for starting from sensor data and going directly into planning and behavior prediction. For example, last year, Best Paper Award at CVPR was UniAD. So we really believe this is an interesting approach and very promising. So we wanted to make sure that people are able to use the Waymo open data set to solve that sort of problem. So last year, as I said, we released LiDAR data for the 1 second of history that you get in the motion data set. And this year we have released camera embeddings coming from a VQ-GAN model. So we took this approach because obviously having the whole camera images would have been very, very large in size. So we thought that it would be easier for users to just have embeddings coming from this model that we trained. And this has a very lower construction loss, so it basically contains all the information that you need to solve a certain task. So along with the data set, there are also a series of benchmarks that we have attached for the different tasks that we think are important for the autonomous vehicle research community. And these, we believe it's the most comprehensive set of tasks and benchmarks that is out there in the wild. And some of them are pretty mainstream, like motion prediction, but some of them were also pretty novel, like, for example, 2D video panoptic segmentation, pose estimation, the occupancy flow, and sim agent were something that it was pretty novel all the time when we released that. I would also like to point out that this is a very long-standing set of benchmarks. So the motion prediction, for example, we've run for 4 years in a row. So it's good to see how much the research community is like approaching this problem and seeing improvements over the years is great. So I would also like to point out another piece of software that we released last year. So along with the data set and benchmarks, we also believe that tools are really important for the research community because otherwise you're not able to solve those problems. And one of the tools that we thought it was really important to have is a simulator. So starting from the motion data set type of format of data, so we have your bounding boxes moving around. You want to simulate this with different agents taking control of different objects. So last year we released Waymax, which is a lightweight research-oriented simulator to solve specifically planning and sim agent problem. It is fully differentiable, so you can backprop through it. It's hardware accelerated, so you can use a GPU or a TPU and you get a nice boost in performance. And it's multi-agent, so you can have multiple policies taking control of multiple objects at the same time. It is natively connected to the Waymo Open Motion dataset, so it's just a plug and play thing, and you can use the whole of the Open Motion dataset, which is great. And it's designedly, and it's written entirely in JAX, which makes it very easy to use external libraries and tinker with it if you want to. So we released this back at the end of last year. We got a lot of interest from the research community, and we're really proud of that. So we're continuing to work on this tool and to make sure that this helps more in the planning sort of tasks. We are releasing by the end of this year the route for the autonomous vehicle, which means, you know, at that you're going to know the Waymo driver. We're going to provide the information of where it was supposed to go, basically. So all said that, I want to deep dive a little bit into the challenges that we had this year. So it's 4 of them: motion prediction, occupancy and flow prediction, sim agents, and 3D semantic segmentation. I would like to start by saying that I'm really proud of the results this year and the number of participants and the traction that we got on the challenges. It's always a nice thing to see year over year. We got a total of 94 participating teams, more than 700 total submissions over the 4 challenges, 46 leaderboard entries, and more than 10 countries participating. So I would like to thank all the participants and their great work. It's really great to see that over the years, a lot of these benchmarks are improving the state of the art consistently. And we're really proud of the quality of work that has been submitted so far. We are publishing the reports of the winning teams on the Open Dataset website and on the workshop website. So you're gonna find all of those very easily at those links, I think. And yeah, said that, I'm gonna give the mic to Scott, who's gonna talk about the motion prediction challenge.
Thanks, Nico. I'm Scott. I'll be presenting the motion prediction challenge and the results for this year. So at a high level, the goal of the motion prediction challenge is to predict the positions of up to 8 agents for 8 seconds into the future, given the agent history and scene data for the past 1 second. And I'll get into some more detail about that. But first, I'd like to thank all the participants from the challenge this year. We had great participation, and we appreciate all the work that went into it. This is the 4th year that we've held the challenge since starting in 2021. As Nico mentioned, we've added this year camera embeddings to the data set as used for inputs to the models. And we've also updated our MAP metrics. We've tried to improve the trajectory bucket balancing and some of the corner cases. So to give you a feel for what the data looks like for the challenge, here's sort of a typical scene. We provide HD maps, and we provide 3D bounding box labels for 3 different types of agents. We have vehicles, cyclists, and pedestrians. We also provide labels for traffic light states, and we also have labels for interactions between agents. Not pictured here, we also have LiDAR data as input and the camera embeddings. So some quick stats on the data set. We have 574 hours of unique motion data. It covers 1,750 kilometers of unique roadways collected from 6 cities. Each of the examples is specifically mined to have interesting interactions. And we compute the perception label boxes in an offline in the data center so that we can devote more compute power rather than just computing what we compute on the vehicle for higher accuracy. And then in the last few years, we've added LiDAR and camera embeddings. So here we see a scene, an example from the training data set where we've got 2 vehicles trying to make unprotected left turns. And the goal or the task for the challenge is to take the first 1 second of this data and predict the trajectories of the agents in the scene for the next 8 seconds. And so in this example, there are three vehicles to predict. There can be up to 8 agents of any object types. And so because motion forecasting is sort of inherently multimodal, the models can predict up to 6 trajectories for each of the objects, and each with a corresponding confidence score. And then we use a suite of metrics that we provide on the leaderboard for each of these. The challenge winner is determined by a metric called soft MAP. And the soft MAP metric determines true positives using a set of lateral and longitudinal thresholds. These thresholds are scaled according to the speed of the object. And then we compute these buckets over 8 different trajectory type buckets, as well as 3 object types. And then we compute an MAP score over there. The full details of this metric are on our website for the Open Dataset Challenge. With that, I'd like to announce the winners of this year's challenge. In first place, we have MTRV3 from DD Global and the Chinese University of Hong Kong. In second place, we have ModeSeek, which is from the City University of Hong Kong, Hanhai Research Institute, and Carnegie Mellon University. And in third place, we have RMP Ensemble from National University of Singapore and Movida PTE Limited. So congratulations to all the winners.
Hello everyone, thanks for the invitation for the organizer of Waymo Open Dataset team. I'm Chen Shi from the Chinese University of Hong Kong, Shenzhen. In this presentation, I will introduce our solution to the motion prediction challenge. Our framework MTL v3 builds upon the state-of-the-art motion prediction method MTL++ and offers improvements in sense encoding and trajectory decoding. At first, let us briefly review MTL++, giving past states of agents and rule maps. An encoder network encodes sense context and generates sense tokens. Specifically, query-centric self-tensioner is adopted. For each query token, it first converts some of the things to query's local coordinate system and then utilizes KN algorithm to collect K neighborhoods, which serves as keys and values. This symmetric encoding of sense context allows the encoded features to be used for predicting the motion of any input agent. After sense encoding, a motion decoder network is adopted to predict multimodal future trajectories. To alleviate the burden of prediction, MTL++ uses K-means algorithm to cluster 64 predefined anchors from GT trajectories of training data, as shown in this figure. Intention queries are then initialized from anchors through MLP and then aggregate context features from the encoded sense tokens through a set of decoder layers. Moreover, MTL++ introduces a mutually guided intention query module to model the interaction among intention queries. Based on this powerful baseline, our framework offers improvement in two aspects. Firstly, we incorporate rule data to provide fine-grained semantic information. Secondly, we utilize the involving and distinct anchors to promote models' regression capability. In Orange motion prediction pipeline, we mainly focus on abstract representation of the things, including bounding box, heading, velocity of agents, as well as HD maps, which depict static road graph. However, rule sense data can provide more detailed information about the things, such as agents missed by perception module, dynamic sense context like road walk, and more rich road graph like traffic cone and traffic guardrail, and so on. So we incorporate data point cloud to reconstruct the environment and complement the map information, as well as extract some important real-time context. To efficiently encode data point, we mainly follow the pipeline of MGT. Firstly, for each focal agent, we transform the point cloud data into its local coordinate system based on its position and heading. Secondly, we use a data segmentation network to extract voxel features and generate semantic labels for each voxel. Then to further enhance the representation, the one-hot encoded semantic labels and the voxel positions are concatenated with the orange features, resulting in 58 dimensions features. Finally, we apply sparse energy pooling operation to pool the voxel into BV space, resulting in data tokens with a grid size of 1.6 meters. In decoder network, we use a dynamic strategy to gather related data tokens for each focal agent. Specifically, we define 3 target positions, including a current position P and 2 feature positions predicted from the velocity and prior knowledge. Then KN algorithm is employed to collect data tokens for cross-station in decoder layer. The updated pipeline is shown in this figure. In vanilla MTL++, the anchors are fixed, which limit the model's regression capability. So we utilize the involving and distinct anchors proposed in EDA. Starting from predefined anchors, EDA updates them based on the endpoints of predicted trajectories in decoder layer. This year, the sense-specific anchors. Then MS operation is applied to select distinct anchors to avoid gradient conflict among similar anchors. And finally, in the experiments, we can show that our MTL v3 achieves the first place in this year's motion prediction challenge. That is the end of our presentation. Thanks for your listening, and more information can be found in the technical report.
Great. And with that, I'll turn it over to Reza for the occupancy and flow challenge.
Yeah, thank you, Scott. Next, you're looking at the occupancy and flow challenge, which is defined on the same data set as the previous challenge, the motion challenge, introduced by Scott. So I'm Breza from the Waymo research team, and I'll be giving an overview of the challenge. And following that, you'll see 3 very short videos from the winning teams. Like the motion challenge, the inputs to the model are past agent states, but the predictions are bird's eye view occupancy and flow of agents in the future. This year, the motion dataset also includes LiDAR and camera tokens. The winning submissions that are shown here didn't use these new features, so there's an opportunity here to improve the state of the art by adding these additional inputs to the model. So in the motion dataset, each scenario has 1 second of history over 11 time steps and 8 seconds of future over 80 time steps. For the occupancy and flow challenge, we predict a total of 8 snapshots from these 80 future time steps. So not every time step. And that's mostly to limit the size of the submissions that we need to receive. And these snapshots are 1 second apart. There are 3 tasks or 3 disjoint predictions in this challenge. The first task is to predict the future occupancy of agents, which are already observed. The second task is to predict the future occupancy of agents, which are currently occluded and appear at some point in the future. For example, as you see in the middle figure, the ego vehicle, as it gets closer to the intersection, it may get to see some additional agents. The third task is to predict flow fields capturing the motion of all agents. In the visualization on the right, we see a set of flow fields, and the colors here represent the direction of magnitude of motion at each point. The metrics evaluate occupancy predictions using AUC and soft IOU metrics. Flow is evaluated by averaging the endpoint errors of the predicted flow vectors. But the main metric for the challenge for the leaderboard is flow-grounded occupancy, which warps occupancy according to the predicted flow vectors and compares that with the ground truth. So this metric requires both occupancy and flow to be correct. And the 3 winners for this year's challenge are DOPP from Nanyang University in Singapore, STNet from Seoul National University in Korea, and HGNET from Tongji University in China. Next, you're going to see 3 2-minute videos from these 3 winning teams.
Hi, I'm Hao Chen from NTU Singapore. Today it is an honor to present our work, DOPP, Differentiable Integrated Occupancy Flow Field and Motion Prediction, which received the first place in this year's Occupancy and Flow Prediction Challenge. Our team members are all from Automan Research Lab in NTU, directed by Prof. Chen Lu. Our research focus are autonomous vehicle system and human-machine collaboration. The general idea of proposed DOPP is to integrate the occupancy flow field prediction task with motion prediction, so that both prediction format interact in social consistent manners. We leverage the query-based modular code design upon a portion of our preceding work, HPP. We directly use STNet for scene encoding, which is the second place submission of this challenge in 2022. We proposed the MS-Occ to perform aligned occupancy decoding. To be specific, the MS-Occ used cascade transformer-based occupancy decoding for each future step. We designed agent condition occupancy decoding task for observed occupancy. Furthermore, a multi-stage integration between occupancy and the motion features are adopted with designed swing multi-head cross-attention module, or SWMCA, for local integration. DOPP performs state-of-the-art results in occupancy and flow leaderboard and gets substantial prediction improvement compared with our previous StretchNet submission. If you are interested in more resources of StretchNet and our work based on HPP, please scan the QR code below for more information. Thank you.
Hello everyone, I'm Dairhan, and this is our occupancy and flow prediction solution for 2024 Waymo Open Dataset Challenges. We are a team from Seoul National University of Science and Technology and Chungnam National University. First, let me introduce our input representation. For a given scenario, we extract 11 frames from the past 10 frames to the current one. Each frame includes agent and static features, and they are 256 by 256 bird's eye view feature maps. Each feature map has 3 channels, therefore the final input features are two 4-dimensional tensors, and their shapes are 11 by 256 by 256 by 3. This is our model overview. From input features, the encoder generates multi-scale features. The aggregator defines these feature maps, and then the decoder combines these features and generates one feature autoregressively. Lastly, the prediction head estimates the final occupancy and flow feature. This is our encoder structure. We base our encoder on the CA-former S18 backbone, but because it is designed for static images, we add temporal convolution blocks to handle temporal input. Next, let's talk about the decoder. This is part of our overall decoder based on one frame. Features are viewed horizontally from coarse to fine for multi-scale information. At the same time, they are viewed vertically, and this is an autoregressive process because it keeps adding a new feature from the start frame to current frame. Each horizontal loop produces one frame feature. Of course, the total number of these features is 8. They are stacked and then passed to the prediction head. This is our loss design. We use 3 losses. This is our implementation details. This is our research and visualization. You can find detailed solution in our technical report. Thank you.
Hello everyone, I'm Zhang Chen from Tongji University. It's my honor to present our third place solution to the Occupancy and Flow Prediction Challenge this year. This is the outline of my talk today. For the framework of our method, we utilize multimodal input, including vectorized and visual input, along with a transformer-based encoder processing this input to generate context tokens for subsequent modules. For the 3 prediction targets in the challenge, we designed a hierarchical aggregator and decoder. Flow is set as the first prediction target, and its high-dimensional features are used as guiding features for the subsequent layers, as they represent the change of occupancy. Occluded occupancy is the last prediction target, guided by both flow and observed occupancy. This approach leverages visible information features for reasoning and prediction of completely occluded objects. Specifically, we proposed the feature-guided detention module, FGAT in short, to leverage guiding features during the feature extraction process. Additionally, for temporal prediction target, to enhance temporal relevance and consistency of the prediction output, we adopt the time series memory framework. This framework updates the temporal information hidden state within the time series memory container and outputs feature information from all previous prediction time steps for feature fusion. During training, we use focal loss and cross-entropy loss for occupancy and smooth L1 loss for flow. Here are partial ablation experiments and quantitative results, demonstrating the effectiveness and advancements of our method. Thank you for listening, and if you have any questions, please refer to our technical report or feel free to contact us.
Okay, hi, it's me again. So this time I want to talk to you about simulated agents and the simulated agent challenge that we hosted again this year. So it's the second year in a row. So I would like to start from the very beginning. When you have an autonomous vehicle, what you want to do is to test it, obviously. But testing in the real world is quite expensive. So you need a safety driver, you need an actual car. So it's not really a scalable approach. What we usually rely on doing is testing in simulation before testing in the real world. And the main problem is that when you have a simulator where you test your autonomous vehicle, you want the simulator to be as realistic as possible because you don't want the car to learn something that is not would not happen in the real world, actually. And so this problem of realism is at the core of simulated agents and their evaluation. So simulated agents is just an agent that takes control of the dynamic object in a scene when you are in a simulation, and its objective is to have as realistic as possible behavior while interacting with the autonomous vehicle. In defining this problem, we are actually going with the canonical split between a perception system and a behavior system. So sim agents are defined at the level of a planner. So there is no central simulation, which obviously makes things more end-to-end and interesting, but also more complicated. So we thought of going with this approach. And the task in the challenge is to, starting from a 1 second history, you want to simulate forward for the 8 second that you have in the Waymo open dataset. So we published a paper about this benchmark last year at NeurIPS. I left a citation there. It's much more complete than what I'm going to say in this presentation, so please have a look. The main question now, it's like, how do you actually evaluate these sim agents? And our approach has been one of distribution of realism. So you want to have the distribution of behavior that you saw in the real world, and you wanted to compare it to the distribution of behavior that you saw in simulation, and you want those two distributions to match. Obviously, measuring what behavior is, it's a bit of another difficult problem. Our solution is to come up with several sub-metrics that we divided into 3 categories: kinematics, map adherence, and interaction. So kinematics is just like how you move, map adherence, how you move on the road, and interaction between different type of agent and on the road itself. We made several changes in 2024 that we are proud of. So some fixes in making things more stable. We changed the metametric weights, which made things more informative. And those are some simulation from the top scoring for submissions. I mean, they're not moving, so they're not really informative. So with this, I would like to announce the 3 winners of this year challenge. So we have in the first place BehaviorGPT. So it's a decoder-only model for simulation. We're gonna hear a presentation from them in a video. The second place goes to VBD, and the third place goes to Traffic Bots V1.5. We're also gonna hear a presentation from Google DeepMind team that was not included in this list of winners for obvious reasons, and they're gonna present in person here. So first of all, let's go into this video.
In this talk, we introduce BehaviorGPT, a decoder-only autoregressive transformer that simulates agent behavior via next patch prediction. Validating the safety of autonomous driving system via simulation has become more and more attractive, which enables rapid testing in diverse driving scenarios simulated at low cost. This work focuses on simulating the behavior of agents such as vehicles, pedestrians, and cyclists in the digital world, which is critical for efficiently validating and iterating behavior policies for autonomous vehicles. A good simulator should be realistic, matching the real-world distribution of multi-agent behaviors to support the assessments of autonomous vehicles' ability to coexist with humans safely. We formulate the agent simulation problem as next patch prediction. By enforcing models to autoregressively generate the next patch containing multiple time steps, which requires understanding the high-level semantics of agent behavior and capturing long-range spatial-temporal interaction. We prevent models from leveraging simple shortcuts during training. Here is an overview of our modeling framework. We adopt relative spacetime representation to equip the model with roto-translation invariance in space and translation invariance in time. Under this representation, we embed coordinate-independent attributes for agents and map elements, then utilizing relative spatial-temporal positional embedding to effectively maintain the spatial-temporal relationships. On top of this, we conduct patching operation for agent states and tokenize the map elements, feeding the agent and map embeddings into a decoder-only transformer that operates at the patch level. The transformer decoder consists of 3 attention modules, including a causal self-attention in the time dimension, an agent map cross-attention, and an agent-agent attention. Based on the attention output, we employ teacher forcing to train the prediction head to perform next patch prediction. We assume the next patch distribution to be marginal and multimodal, parameterizing it with a mixture model. For each behavior mode, we use an autoregressive GRU to generate the next state step by step without relying on any teacher forcing. To train BehaviorGPT, we employ the negative log likelihood loss on the factorized distribution as formulated previously. Note that each ground truth trajectory patch is transformed into the viewpoint of its previous patch. Our BehaviorGPT achieves outstanding performance on the Waymo OpenSim agents benchmark, especially in terms of the mean ADE and the map-based metrics. Notably, our model only contains 3 million parameters, which is much more lightweight than other solutions. Our experiments show that using a larger patch size can improve the performance, which demonstrates the effectiveness of the next patch prediction paradigm. We also know that the frequency of conducting next patch prediction during inference can impact the performance. In our experiments, we found that conducting next patch prediction every 0.5 seconds works the best. In summary, we propose a decoder-only autoregressive transformer for agent simulation, which is simple and parameter efficient. Training the model to predict the next patch instead of the next state enables high-level scene understanding and long-range interaction reasoning in space and time, thereby improving the realism of simulation. During inference, the frequency of conducting next patch prediction also matters. Thank you for your listening.
Thanks a lot. And now we're going to have the presentation from Xinghua. You want to come here? Yeah.
Hi. So our approach is called model predictive simulation using structured graphic models and transformers. This is John working with my colleagues from Google DeepMind. So we all know that a lot of great work on building bottom-up neural networks for motion prediction. They have achieved a great success, but we took a different approach. We think of how can we add top-down knowledge and make it better. And we use the graphic models. We think it can bring better controllability, robustness, also reliability. Also, we think PGMs there can act as guide rails against hallucination and false predictions. Also, more important, what we build is orthogonal and complementary to any of the existing work. You can just take your network at hours and it will help you doing those simulations. This is our model. It's shown as a fact graph. So the nodes, circular nodes, they're actually states of each agent at every time step. And we add a bunch of factors. So kind of energy functions over those different states or different pair of states. We encode, so the actual energies that we encode our priors like motion smoothness and linearity of motion, collision avoidance, etc. We also have factors that can encode as the output of the motion prediction network. So everything is coherent inside of one single framework. Then we can sample from this model. That's how it works. Well, first, we have a history, which is the scene and the age in the past 1 second trajectory. So we put it into a neural network for both prediction. In our case, we use MTR, which is because it's available as a public open source project. Then it essentially generates a proposal, list of proposed trajectories about the future rollouts. It may be suboptimal, it may collide, it may be non-smooth. So we put that into our PGM model, which will give you a smooth trajectory, also give you a score over all those possible rollouts and describing its compatibility with our prior. Then we can use this score to sort the mean as an example from it. So once we get the output, we take the immediate next step, append it to the history, then we repeat. So that's why our model is so-called model predictive. So it's a kind of planning to the deep future, take one step and replan again. We perform really well on the same HGNET challenge. We are among the high tops ranked participants, and we score really well on those important metrics as off-roading and collision, etc., because those are where we included our prior knowledge. We implement our modules in JAX and make it work with MTR, which is open source project. This is just an example of multi-model diverse behavior generated by our model. You can see this car going left, a car going right. You can see another car which is merging or which is following. Those are all created and simulated. This is also an example of how our model can generate common traffic behaviors like unprotected left turn, merging, yielding, etc., etc. So to sum up, we build a top-down prior-knowledge-based approach that can work with bottom-up data-driven neural network and yield really good results. Our approach is also going to complementary to existing bottom-up approach, and we can use this and shown to generate realistic and safe and diverse simulations for traffic simulation. Thank you.
Thanks a lot, Xinghua. Now we're going to hear from Zhenpei on the 3D semantic segmentation challenge.
Hello. Hey, everyone. I'm Zhenpei Yang from Waymo Research. Now I will be discussing the final Open Dataset challenge of this year, the 3D semantic segmentation challenge. We initiated this challenge back in 2022. The task of this challenge, wait, is this mic working? The task of this challenge is to produce a semantic class labels for each LiDAR point, given one or more LiDAR scans and the corresponding camera images. It supplements other perception tasks, such as 3D object detection, by providing a more fine-grained understanding of the scene. We provide point-wise semantic labels for 23 classes in a subset of the perception dataset, which amounts to, in total, 32,000 label frames and 4.7 billion label points. To evaluate performance, we compute the IOU score for each class and then compute the average across those IOU scores. This year, we focus on further enhancing the label quality. For example, we corrected some false positive cases of the motorcyclists, which were wrongly labeled as cyclists or motorcycles in our previous data release. We also reduced inconsistency in background labels across frames. Overall, we believe these improvements led to more accurate evaluations. Here are the results of the top 3 methods in this year's challenge. First place is PTV3 from the University of Hong Kong, Shanghai AI Lab, National University of Singapore, and Nanyang Technological University. Second place is MixSeg 3D from Marvel Technology. Third place is VFuse Set 3D from Vision RD. All 3 methods achieve over 90% IOU in categories such as buildings, tree trunks, and workable surface. However, we can see there is still a lot of rooms for improvements for future participants in categories like lane markers, motorcyclists, and traffic lights. Looking ahead, we see several promising directions for future participants. This includes, but not limited to, integrating large pre-trained foundation models and utilizing self-supervised joint training with 1D LiDAR data. Now I would like to hand over to this year's winning team to discuss their method, Point Transformer B3. I also encourage you to check out the reports from the second and third place team, which I found to be also very insightful. Thank you.
Hi, everyone. My name is Xiaoyang. I'm a PhD student from the University of Hong Kong. Now let me briefly introduce our new generation of point transformers. The first solution for the 2024 Waymo challenge in semantic segmentation. PDV3 achieves sought-out performance on over 20 downstream tasks across indoors and outdoor, including semantic segmentation, instance segmentation, object detection, and data efficiency. We expand the kernel size from 16 to 1024, but still not reach a limitation. Compared with V2, V3 is 3 times faster in latency and 10 times more efficient in memory, which is even better than HGNET, known for its efficiency. PDV3 is motivated by our exploration of large-scale 3D representation learning technology, enhanced with multi-dataset joint training by PBT, another of our work set by the CVPR. We found that SparseUNet, which was proposed 5 years ago, is even stronger than point transformers, but still remain efficient. However, point transformers fail to enlarge the training scale due to the restriction on model efficiency. The observation encouraged us to assume that model performance is more significantly influenced by scale than complex design detail. We should prioritize simplicity and efficiency over the accuracy of certain mechanisms. Then the efficiency will further enable scalability, which makes the sacrifice in accuracy ignorable and brings stronger performance. This formulates our scaling principle for backbone design. So what's the starting point for examining our scaling principle? We benchmarked the forward latency of the point transformer version 2. We noticed that the k-nearest neighbor query algorithm, which provides accurate neighbor points for point-based methods, take up 28% forward time due to difficulty in parallelization. However, do these accurate neighbor points really matter for good local attention? The answer is not. Attention is adaptive, so we can trade the accuracy of neighborhood for better efficiency. Further, inspired by Occupancy and Flatformer, we decided to break the traditional paradigm, which treats point cloud as unstructured data and seek a way to transfer the point cloud to 1D structured data while still maintain the spatial proximity to some extent, so that we can benefit from the convenience of structured data and enable a huge leap in model efficiency. That is the serialization of our point transformer version 3. Specifically, we introduced space filling curves, paths that go through every point within a higher dimensional discrete space and preserve spatial proximity to a certain extent. The serialization of point cloud is achieved by sorting the points with the order traversed by the space filling curve. After that, the original unstructured point cloud turned to a structured 1D data. Then after the necessary padding operation, we can easily enable patch grouping for local attention with reshaping operation and utilize high optimized flash attentions for structured 1D point clouds. Another issue worth noting is that the relative precision encoding, which is necessary for local attention, also take up to 26 forward time. We found that a simple prepend of sparse convolution is a good replacement for relative precision encoding. For some cases, sparse convolution is hard to deploy, so I suggest use O-tree-based convolution as a replacement. Peng Shuai, as the author of OCN, has a one version fully written with PyTouch. So specific for this Waymo challenge, we launched the extreme version, which views additional path-through frame as a reference and adopt a non-clipping proxy, which used to be crucial for sparse convolution. Finally, coupled with the model ensemble strategy, we achieved the strongest performance in Waymo semantic segmentation benchmark. The detailed setting and performance is as follows. Finally, we achieved 74.8% MIOU on the validation split and 72.8% MIOU on the testing split on the Waymo dataset. A more detailed illustration is available in our oral presentation and tutorial for point cloud processing. Please scan the QR code for detailed information. Thanks.
Okay, thanks a lot to all the participants. This is the end of the Waymo content with the last self-promotion. So we have a talk tomorrow by Drago, our head of research, at the workshop on data-driven autonomous driving simulation. There's a paper presentation on Thursday about most, and please stop by our booth. We're very happy to talk to any of you about like career opportunities and why we are excited about Waymo. So yeah, please reach out and get there. So yeah, thanks a lot for being here. And yeah, with this, I hand over to Alex.